Good morning, my dear students. My name is Mr. Jude Gessi, your ICT teacher. I'll be taking you on the topic logic gates. Now, before we proceed, we'll be looking at some of the objectives that we're expected to achieve at the end of this class. Now, the first objective, you should be able to define logic gates. The second objective, you should be able to state the three standard logic gates or basic logic gates. Number 3, you should be able to state the alternative logic gates. Number 4, you should be able to identify and draw logic diagram and truth table for each gate. Now we'll also continue by defining logic gates. Now, first of all, logic gate is a building block of digital circuits. Most logic gates have 2 inputs and 1 output. Now, for instance, the socket you have in your house, your light switch, at every point in time is in one state. It's either is off, which is logic 0, or is on, which is logic 1. Okay. So we'll also look at these types of logic gates. Now we have 3 major types of logic gates. We have the basic logic gates, we have the universal logic gates, and we have other gates. Now the 3 standard logic gates or the basic logic gates, we have 3 of them. We have the AND gates, we have the NOT gates, and we have the OR gates. Now this universal logic gate is derived from the standard logic gates. We have 2 of them here, the NAND gate and the NOR gate. Now the NAND gate simply means not AND. It simply means not AND. The N simply means not AND. So this NAND gate is a combination of the NOT gate and the AND gate. Why the NOR gate is the combination of the NOT gate and the OR gate. Okay, so we have other gates. We have the exclusive OR gates and we have the exclusive NOR gates. So we'll be looking at some of the hints that will help us to draw the truth table for each of these gates. Now, in the first place, in OR gates, the output is true. When I say the output is true, it means that the output is high, or you say the output is 1. So in OR gates, the output is true or 1 if both inputs are true, or one of the inputs is true. Now, so long as you have a true value, like for instance we have 0 and 1, the output to be 1. 1 and 0, the output to be 1. 1 and 1, the output to be 1. But unless you have both inputs to be false, that's when you have a false value as the output. So in OR gates, the output is true if one or both inputs are true. Now in AND gates, the output is true if and only if both inputs are true. In NOT gates, the output attains the state 1 if and only if the input does not attain the state 1. So what it simply means that in NOT gate is simply an inverter. If the input is 1, the output definitely will be 0. And if the input is 0, the output definitely will be 1. So now, like I told you before, the NAND gate is the reverse of the AND gate because of the negation, the NOT gate. And I told you that is the combination of both the NOT gate and the AND gate. So if it's not AND, that means in AND gate, if the output is 1, in NAND gate, the output will be 0 because of the inverter. Now, in NAND gate, if the output is 0, in AND gate, the output will be 1. Okay, so in NAND gate, the output is false if both inputs are true. In NOR gate, the output is true if both inputs are false. When I say are false, it means if they are 0. In exclusive OR gate, the output is true if exactly one of the inputs is true. So in this gate now, the output can only be true if one of the inputs is true. Now, if we have 0, 1, the output will be 1, which is true. Now if you have 1 0, the output will be true, which is 1. Now but if you have 0 0, the output will be 0. If you have 1 1, the output will be 0. That is why we said if exactly one of the input is true. Now in exclusive NOR gate, you also agree with me that this is the inverse of the exclusive OR gate. So in exclusive NOR gate, the output is true if both inputs are true or false. Okay, so let's look at the AND gate. Now looking at this, the first thing you see there is the logic diagram. This is logic diagram for AND gate, and this is the truth table. And I want to point out something clear here. Now in drawing a truth table, remember the inputs A and B are always the same for all the gates. I repeat myself, the inputs A and B are the same for all the gates. It is just a standard. Now we have input A, or input A, we can have 0011, or we have 0101. The input B will have 0011 or 0101. But it must be is a standard. It does not change. So either you use this 0011 that is in input B in input A, and use 0101 in input B. It doesn't matter. What matters is the combination. It must be the same. It must be the same. Okay, so here we have 0101, and input B will have 0011. Now look at the output. Because it's AND gate, we have 0 and 0. It's just like when you are doing multiplication. 0 and 0, the output gives you 0. 1 and 0, the output gives you 0. 0 and 1, the output gives you 0. 1 and 1, the output gives you 1. So it's like when you are doing multiplication. That's the technology in the technology in a AND gate. So that is how it's being derived. So let me tell you something. Just like in your basic mock exam, you were given truth tables to identify the gates, and if you don't know this, you cannot identify the gate. Now in your exam, the questions can come in various forms. You can be given the logic diagram to identify the gate, or you are asked to draw so gate, or you are given the truth table to identify the gate. So that is how question can come in various forms. So that is why it's so expedient that you know the logic diagram and also the truth table. Like I said before, the inputs A and B are the same. They are standard for all the gates with 2 inputs. Now let's look at this one, the NOT gate. Like I told you before, the NOT gate is the only gate that has 1 input and 1 output. Now look at this, input A. Now if it's an inverter, if input is 0, the output should be 1. And if the input is 1, the output should be 0. So it's a very straightforward gate. Now let's look at the OR gate. First of all, you look at the logic diagram. This is the logic diagram. And remember in AND gates, the Boolean expression can be written as maybe A equal to A dot B, or C equal to A dot B, or anything equal to A dot B. Now, in NOT gate, the Boolean expression can be written as A equal to A bar, or B equal to B bar. That is the inverse of B or inverse of A. Now, in OR gate, the Boolean expression is written as C equal to A plus B, or Z equal to A plus B. Any number can come in. What matters is the Boolean expression A plus B. And in this OR gate, you look at the logic diagram here, and you are seeing the truth table. Now we also have the inputs A and B. Input A here will have 0011, and input B will have 0101. I told you is a standard. is the standard for all the gates. The only difference is the output. So if you are faced with such a challenge and you're asked to identify the gate, what you look at is the output. Don't look at the input A and B, because they are the same for all the gates. So what you look at is the output. Okay, so here we have, and in all gates, I told you that so long as there's a true value, the output remains true. So long as one of the input is true, the output remains true. So that's why we have false or false is false. False or true is true. True or false is true. True or true is true. Remember, when I say true or false, when I say false, I mean 0. Or when I say output is high, I mean 1. If output is low, I mean 0. If I say false, is 0. If I say true, is 1. Please understand this. They can give you in various forms. Okay, so we look at the NAND gates. The NAND gates. Like I told you before, the NAND gate is just the opposite of AND gate because of the inverter. So in AND gates, where the output is 1, in NAND gate it will be 0. So here we have 0 and 0. It will be 1. So the output, like I told you, if you go back to your NAND gate, you find out that in this case 0 and 0 will give you 0. But in NAND gate is 1. So it is just the inverse because of the inverter. And when you look at the Boolean expression, you see C equal to A dot B bar. But out of NAND gate, what you will see there is C equal to A dot B. But because of the inverter, which is that bar on top, we'll have A dot B bar. So this is also the logic diagram. We have, you see the bubble there. There is one bubble. That bubble also signifies inverter. Okay. So let's look at the NOR gate. It is still the same thing. The NOR gate is just the opposite of the OR gate. Okay. Now, you also see the logic diagram. And you see the inverter there. That is why the Boolean expression now turns C equal to A plus B bar. A plus B bar. But that of OR gates, it is just C equal to A plus B. So the bar at the top simply shows that there is an inverter, which is the bubble you are seeing. Okay. So we now say 0 nor 0 will give us 1. 0 nor 1 will give us 0. 1 nor 0 will give us 0. 1 nor 1 will give us 0. It is just the inverse, the reverse of what we have in OR gates. Now we have another powerful gate here, exclusive OR gate. It can be written as EXOR gate or XOR. You can see it in either form. So this is, you can see this is the logic diagram, and you see the difference between this and the OR gate is the extra line you are seeing. Okay, so now, and when you look at the Boolean expression, we have C equal to A exclusive B. It's pronounced A exclusive B. So you see that 0 with plus sign inside is called exclusive. That's the sign. So here we have C equal to A exclusive B. Now, that letter C can be anything. It can be Z equal to A exclusive B. So we now look at the truth table. Now, I told us in the beginning that in exclusive OR gate, the output is true if exactly one of the input is true. If you can recall that in exclusive OR gate, the output is true if exactly one of the input is true. And I told you that if we have 1 and 0, the output will be true. If we have 0 and 1, the output will be true. But if we have both inputs to be true or both inputs to be false, the answer will be false. Okay, let's look at this one. We have the exclusive NOR gate, which is the opposite of the exclusive OR gate. And now if you look at the diagram, you will still see the bubble that signifies the inverter. That bubble there is the inverter. And that's why when you look at the Boolean expression, we have C equal to A exclusive B bar. While in exclusive OR gate, we have A exclusive B. But in exclusive NOR gate, we have A exclusive B bar. That shows that there is an inverter. So this exclusive NOR gate is the opposite, the inverse of exclusive OR gate. So in exclusive NOR gate, the output is 1. The output is true. The output is high if both inputs are true or false. Just like in exclusive NOR gate, we said that the output is true if exactly one of the input is true. So in this case, the output is true if both inputs are true or false. That is, if both inputs are 0 or 1. Okay, so we look at all the gates together. Now we have the first one. The first one we have here is called a buffer memory. It's called a buffer memory. It looks like the inverter, but it doesn't have the bubble. Look at it very closely. It looks like the inverter, but it does not have the bubble. Now when you look at the logic diagram, you find out that the input A is the same thing as the output. Input, like, see, we have input 0 and the output 0. We have input 1 and output 1. But if look at the inverter down, when you look at the inverter, you see that if output is 0, the input will be 1. And if the input is 1, the output will be 0. So, but that of buffer memory, the first one we are seeing there, the output is the same as the input. Okay, now let's look at the AND gate. It's just a summary. Look at the diagram and the truth table. You find that look at this diagram, and they will have the truth table here. You will see the OR gates. This is the diagram, and this is the truth table. We have the exclusive OR gate, the diagram, the truth table. We have the inverter, the diagram, the truth table. We have the NAND gate. You can compare them as you are looking at it. You see that is the inverse, the opposite of AND gate. We have the truth table and the logic diagram with bubble. We also have the NOR gate. We have the truth table, and we have the logic diagram. Then we have the exclusive NOR gate. Look at the truth table there, and we have the logic diagram. Okay, very well. I have little assignment for you. Look at the assignment. And I know you can do it. As you're relaxing in the house, please just play with it. Now you have to draw the logic diagram and truth table for the following gates. The first one will have the AND gate. Second one will have the NOT gate, the OR gate. The third one will have the NOT gate. The fourth one will have the exclusive NOR gate. The fifth one will have the NAND gate. The sixth one will have the NOR gate. The seventh one will have the exclusive OR gate. Please, you are to draw the logic diagram very clearly. Draw the logic diagram and the truth table for each of these gates. Okay, and after you are done, you submit your answer to the email address below: fgcphdgclass@gmail.com. fgcphdgclass@gmail.com. That's the email address you are going to submit it. Please obey instruction. Draw the logic diagram and the truth table for these gates. Submit your answer to the email address fgcphdgclass@gmail.com. All right, my just 3 students, Please see you in our next class. If you have any challenge, do well to drop your question in our Telegram group and I will surely attend to you. Stay safe and observe social distance. Wash your hands with soap regularly under running water for at least 20 seconds. Use alcohol-based sanitizer. Thank you very much. I remain Mr. Jude, your ICT teacher. God bless you. See you in our next class. Thank you very much. Bye.